Video is going to take you back to the topic of radicals. We're going to start with a little review and then we're going to get into a new skill. So you've got all of the notes in topics and the notes are numbered for you. So this particular video is going to use page 1, 2, and 5 of your notes. So let's go ahead and get started, and let's start with a basic review on page 1. So just to go back and name the parts, this is called the index. The symbol itself is called a radical. The number underneath the radical is called the radicand. And if there's no index given, meaning if there's no number written there, then you assume that the index is 2 and you're looking for a square root. And we're always looking for the principal or positive root, and that's what's mentioned right here. We're looking for the positive root only in Algebra 1, positive root only. Okay, so just to go back, and I just wrote down a few of the perfect squares right here. 4 is 2 times 2, so the square root of 4 is 2. 16 is 4 times 4, the square root of 16 is 4. Now 4 itself is also a perfect square, but outside the radical, it's just the integer 4, so there's no need to continue breaking it down as 2 times 2. The square root of 36, 6 times 6 is 36, so that's just simply 6 outside the radical. And 81 is 9 times 9. Outside the radical, it's just 9. And once again, 9 itself is a perfect square, 3 times 3. But outside the radical, it's just the integer 9, so you stop there. And then the other skill that we had learned earlier in the year, we learned how to simplify non-perfect squares. So I would like to go back and talk about that for a few minutes before we catch our new skill. So I've chosen the square root of 72, just to go back and review an old skill. 72, and remember, in order for the answer to be considered in completely simplified form, reduced radical form, no perfect squares remain underneath the radical. So all of the perfect squares need to be removed from the radical. 72 is 36 times 2. 36 is the perfect square. The square root of 36 is 6, and 2 remains underneath the radical. So that would be the reduced radical form of square root of 72 would be 6 radical 2. Moving on to radical 125. Well, this is going to be 25 times 5. 25 is the perfect square, so the square root of 25 comes out, and this might be, some students like to see it presented like this as well. The square root of 25 times the square root of 5. This is the perfect square portion, so it's written as just the integer 5 without the radical symbol. But then radical 5, which is the non-perfect portion, still remains as part of the expression, but it's written with the square root symbol around it. 243. 243 is 81 times 3. 81 being the perfect square. So you could think of that as the square root of 81 times the square root of 3. And since this is the perfect square, it simplifies down as 9, but the radical 3 portion, the non-perfect portion, is still written with the square root symbol around it. And as mentioned above, 9 itself is also a perfect square, but sitting outside the radical here, it's just the integer 9, so there's no need to continue breaking it down looking for the perfect square factor of 9. Now let's move to a new skill. Moving to page number 2 in your notes. So the new skill, first new skill, is going to be dealing with variables raised to powers underneath the radical. So I would like to break a few of these down before we make the rule. So I'm going to show you what this is, and then as I'm doing it, you're probably going to figure out what the rule is as we move along. But the first skill in our revisit topic, or revisit unit with radicals, is the skill of simplifying when you have variables underneath the radical. And we are going to make the assumption that all of the variables are positive. And in subsequent courses, you will learn how to handle this when all of the variables are not positive. But for our purposes, for the remainder of this school year, we're going to assume that any variable that we encounter underneath the radical is a positive, it's representing a positive number. So let's go back. Let's start with Let's start with the square root of x raised to the power of 10. And to break this down and explain it, I would like to go back to exponent properties. Properties of exponents. So if I have x to the power of 5 times x to the power of 5, that's the same number times itself, which represents a square root. And if I add these two together, when the bases are the same, you add the powers together. If I add those two together, I end up with x to the power of 10. So the square root of x raised to the power of 10 is going to simply be x raised to the power of 5 without the radical symbol around it. So this is going to be my simplified expression. And let's move on. Let's look at radical 16. So applying the same thought with exponent properties, x raised to the power of 16 is a result of x to the 8th times x to the 8th. And to apply exponent properties to that, we would have written the base one time, we add the powers together, and that's how we would have arrived at x to the power of 16. So once again, I have the same expression times itself, which is what a square root is. So the square root of x to the power of 16 is going to be x to the power of 8. And I chose 16 on purpose. 16 is a perfect square. I'm not looking for the square root of the exponent. I'm simply looking for, I have to go back and think of exponent properties. And I'm not looking for the fact that 16 is 4 times 4. I'm now looking at the fact that 8 plus 8 equals 16. And let's move on and do the last example before we make our rule. X raised to the power of 24. Well, that could be x to the 12th times x to the 12th. Adding those two together, 12 plus 12, that's going to give me the 24. So once again, it's the same expression times itself, which is representing the perfect square. So the square root of this expression is going to be x raised to the power of 12 outside the radical. So the rule to take away from this, when you have a variable raised to an even power underneath the radical, that even power tells you that this is a perfect square. So when you're simplifying this, and I went ahead and wrote this x to the power of n, if you want to jot this down on your notes, and we're going to assume here that n is an even number. This pink model is going to go with the model that I've typed. The simplified form of this, you would write the x, the variable x, and then the power that you would raise it to would be n divided by 2. You would simply divide that in half. So when the variable is raised to an even power, that represents the perfect square. And then outside the radical, you write the variable once, and you just simply take that exponent number and you divide it in half, and that represents the simplified answer, the simplified form. Now let's look at what happens when you have an odd power. So here, x to the 15th, the largest perfect square factor of x to the power of 15 is going to be x to the power of 14. And then that's going to leave 1x left over. 14 plus 1 equaling 15. So I have to go back to my exponent properties. Remember, when bases are the same, you add the exponents together. I need to go back and recall that and remember that property. And then using the logic from above, 14 is an even number. 14 divided by 2 is 7. And I'm going to have this x raised to the power of 1 that's going to have to remain underneath the radical. So the simplified form here, 14 divided by 2 is 7. And then I have the x that would remain under the radical. The x to the first power would remain underneath the radical. So the simplified expression here is going to be x to the power of 7. And then x to the first remains underneath the radical. Let's look at 9, x raised to the power of 9, and apply the same logic. The largest perfect square factor of x to the 9th is going to be x to the 8th. And since it's to the 9th power, x to the 8th, 8 plus 1 gives you 9. So here's my perfect square because it's an even number. 8 divided by 2 is 4. So that means that my simplified expression is going to be x to the power of 4, and then x to the first is going to remain underneath the radical. And then x to the power of 31, the largest perfect square factor here is going to be x to the power of 30, leaving me with x to the first. And then 30 divided by 2 is 15. So that's going to be x to the power of 15. and then I'll have the lone x that stays underneath the radical. X to the first would remain underneath the radical. So here's a rule to take away from this. When you have a variable raised to an odd power, the way that you would simplify this, and I've written the model here, let's say let's pretend like m is an odd number. So what you would do, your perfect square, you're going to subtract 1 from m, making that an even number, and then you're going to have 1 left over, x to the first left over. The way that you would simplify this, you would write the x outside the radical. 1x is always going to remain underneath the radical when you're starting with an odd power. Let me zoom out just a little bit. And then the power that you would put on the variable piece that comes out, it's m minus 1, and you would divide that in half. So you would divide that in half. So the way that you deal with the odd exponents, you subtract 1 to get the even number, divide that number in half, and then one variable always remains underneath the radical raised to the first power. And then the skill that we're going to work on, we're going to combine this, we're going to combine the numerical piece with our variables. And that's the first skill to take away from the new revisit of this unit, the new part of this unit. And here I've got radical 63. I've got x to the 5th and y to the 6th. So this is a non-perfect square, x to the 5th. However, y raised to the power of 6 is a perfect square. So breaking this out on the inside, 63 is 9 times 7. X to the 5th is x to the 4th times x to the 1st. And then y to the power of 6 is my perfect square because it's an even number. So here are my perfect squares. The square root of 9 is 3. X to the 4th, well, the 4 comes out at half of that, so that's going to come out as x squared. 6 is an even number. Half of 6 is 3. And then all of the non-perfect pieces remain underneath the radical. 7 remains, and x to the 1st remain underneath the radical. So that would be my simplified expression for this. And then moving on to the next example, 84. And I've got x squared, even number, y 5th, odd number. So this is going to be, I'll break this down again like I did the other one. This is 4 times 21. X squared is the perfect square. 5 minus 1 is 4. Leaving me with 1 left over. So the square root of 4 is 2. X squared, well, the exponent 2 divided by 2 just gives me x to the 1st. Here's a perfect square. Divide that by 2. That gives me y squared. And then all of the non-perfect pieces remain underneath the radical. And I'm now going to move to page number 5. And here are the problems on page 5. All this is labeled and numbered in your notes. And I've copied the problems on other paper, so I'm going to work them out as you follow along. And then this will be the only video on this. I feel like this skill is probably pretty straightforward, and you should be able to pick this up. I apologize for some of the variables. They've used every letter in the alphabet here with the problem set. So I'll do the best I can to write neat so that they look like letters and not numbers. All right, so number 18. Number 18 is, did I do this right? 36 times 3, yes, okay, here we go. Okay, so 108, let me just make sure I did this correctly before I get started. Yes, okay, here we go. 108, so 108 is 36 times 3. And then I have r squared, get my camera right. R squared, so this is a perfect square. This is a perfect square. This is not a perfect square. So I've got r squared, perfect square, s cubed. Well, I need to subtract 1 to get the perfect square. And you don't have to show this amount of detail every single time. I'm just doing this because it's a new skill and I need to make sure that you understand where all the pieces are coming from. So here are my perfect squares. I'll underline my perfect squares. So those are my perfect squares underlined in pink, and then my non-perfect squares right here. So I'm going to clean this up. 36 comes out as 6. R squared, well, 2 divided by 2 is 1. And then once again, 2 divided by 2 is 1. And then 6 divided by 2 is 3. So those are my perfect squares coming out. There's square roots coming out. And then what's going to remain underneath the radical would be the 3 and the s. Let's move on and look at number 19. So number 19 is 68, and that's p cubed. That's a non-perfect square. And 68 is 4 times 17. So I've got 4 times 17, p squared, p to the first. So this is going to simplify as 2p and then radical 17p. Perfect square, perfect square, perfect square, non-perfect portions stay underneath the radical. Let's move on and look at number 20. So number 20 is, here's number 20. So number 20 is, let's see, this is 36 times 5. 36 times 5, x cubed, non-perfect square, y to the power of 8 is a perfect square. I'll do this one slow, and then I'll start doing the other ones a little bit faster because I think you probably are starting to get the idea by now. So my perfect square is 6. X squared is a perfect square. Y to the 8th is a perfect square, remembering to divide those exponents by 2. And then the portions that stay underneath would be 5 and x to the first. The non-perfect portions stay underneath. All of the even powers come out at half what they are underneath the radical, and then any numerical coefficients come out as their square root. Okay, let's look at number 21. So 21 is, let's see, this is 36 times 2. 36 times 2, and I've got m cubed. That's an 8 and a 2. So to just go ahead and make this a little bit faster, this is going to clean up as 6. And let's see, that's going to give me 1m, n4, and p. And then what's going to remain underneath the radical would be the 2 and then one of the m's. So anytime you have the variable raised to an odd power, one variable is always going to remain underneath the radical. And let's look at number 22. So number 22, let's see, 27. Okay, so this is going to be 9 times 3. So that's going to be 3 coming out and y squared coming out. And then what's going to remain underneath the radical would be the leftover factor of 3. And this is x to the first odd number, so it's going to stay underneath the radical. Let's look at number 23. And number 23, okay, so number 23 is, and I'll do this one slow. So this is 36 times 7. That's my coefficient broken down. X to the first, odd, not a perfect square. Y squared is a perfect square. This is z cubed. I would think of that as z squared times z to the first. So my perfect squares are going to be the 36, y squared, z squared, all the even powers in the perfect square. So this is going to come out as 6yz, and then the portions that remain underneath, xz and the number 7. So chances are I would write this, I would write it like this, 6yz, and then I'm going to have 7x and z. That's going to be my simplified expression. And let's do number 24 together before I end the video. So number 24, let me fold my paper. Number 24, 392 is 49 times, okay, yeah, I had to break this down. Okay, so 392 is 49 times 4 times 2. That's how I broke it down when I did it by myself. I've got a squared, b squared, c cubed. A squared, b squared, and then c cubed, 3 minus 1. And then that's going, these are my perfect square portions. I've got 49's perfect, 4, even power, even power, even power. And then I'm going to have 2 non-perfect portions that are going to remain underneath the radical when I clean this up. So the square root of 49 is 7, square root of 4 is 2. I'll multiply those together. That's going to give me 49. And then A comes out, B comes out, C comes out. And then what remains on the inside would be the 2 and the C. And I'll stop the video there.